Hi, and welcome back to the Whistlebit Classroom. This is part 2 of pitch stability and airspeed. So when we left off, we had gone through and plotted the lift due to the moment due to the lift on each wing with angle of attack, and we saw that the two lines cross, and that gives us a trim angle of attack. And we noticed that it was stable because if the angle of attack increases, this line shows that there's more nose down moment on the tail than there is nose up moment due to the wing, so that's going to push the nose down and reduce the angle of attack. Or if the angle of attack becomes smaller, we have less nose down than this one is nose up, and so that's going to push it back up and push us back to a larger angle of attack. The question that we left ourselves with was, what happens if the airplane speeds up? We know what happens if the angle of attack changes, but what happens if the airplane speeds up or slows down? All of these have this letter Q, which stands for 1/2 times the density of the air times velocity squared. So Q gets 4 times as big if V gets twice as big. So it can change very rapidly. So we're going to pretend for a moment that, just to keep things easy, that we're going to double Q. So that means that V has to be increased by 40% or 1.41, which is the square root of 2. So that means that everywhere we had Q before, we have twice as much Q. And we said for the purposes of this graph that this moment at its first speed, we're going to call that V1, had a slope of 1 and the tail had a slope of 2. So now if we double that, the wing's going to have a slope of 2 and the tail's going to have a slope of 4. So I'm going to use a different color ink here, and we can draw the wing again at 0 angle of attack. This still has to be 0, even though this is twice as big, but it's going to have a slope of 2 now. So we're drawing the new wing line. It's got a slope of 2, so over 1 and up 2, over 1 and up 2. Let's get that right on the money. That's looking pretty good. Should parallel this line because that was over 1 and up 2 last time. Okay. So this is our new wing moment at V2 at a higher speed. And this one, the slope is twice as big, but this, we said before, when the angle of attack is 0, this stays around. Q's gotten twice as big, so this has to be twice as big. We said before that it was -2, so now it has to be at -4. 1, 2, 3, 4. So the line has to go through there, and now the slope, instead of being 2, we've doubled it, so it now has to be a slope of 4 through this line. So over 1, 1, 2, 3, 4. Over 1, 1, 2, 3, 4. There we go. So there we go. So here's how I'm going to do the tail at V2. Now what you'll notice almost immediately is that they still cross at the same angle of attack. We haven't changed the trim point, even though we're flying faster. We have changed some other stuff. If we go off of our angle of attack by a little bit, the difference between the tail wanting to push the nose down and the wing wanting to push the nose up is bigger. So going faster definitely makes it react differently, but it hasn't changed the trim. The airplane has sped up, but there's no tendency for the nose to pitch up or the nose to pitch down. And that's not the story that we read from the Wright brothers, that the wind is blowing over the tail and pushing the tail down so that the plane pitches up. So what's going on? Well, what's going on is this. You may recall Newton's second law. Sum of the forces is equal to the mass times the acceleration. The forces on the airplane are lift upwards, drag backwards, thrust forwards, weight downwards. The moment we'll ignore thrust and drag, and we'll just say weight. At our first speed, let's say our plane is flying level. If that's true, then that means that lift minus weight is equal to 0, because lift equals weight. Okay? Perfectly good. Second law is satisfied. But then we said we're going to double Q. Well, if we double Q, Q's up here too, that means lift is twice as big. So if we double Q, now we have 2L is equal to W. Well, that's not true, right? We can't say that this is equal to true. We can't say that 2L minus W is equal to 0 anymore, because it's not. We know what L is, we know what W is. We can, though, write this, right? Because this is the actual equation, MA. Before we said MA was equal to 0, now MA is not equal to 0. MA is equal to W minus 2L. In other words, it's non-zero and it's positive. Because L is bigger than W, small negative number, it's positive. That means that the airplane is going to accelerate upwards. If the airplane accelerates upwards, a funny thing happens. Here's our airplane. It's flying this way. It's pointing this way. This is our angle of attack. This is our velocity. But if the airplane accelerates upwards, we now get some velocity like this. This is our new velocity, and this is our new angle of attack. The angle of attack has gotten smaller because the airplane has started to climb. And when that happens, we're down here. And what did we say happens when the angle of attack gets smaller? The nose down, this is the tail line right here, gets smaller than the nose up. And the airplane is now in a region where it wants to pitch up to return to that angle of attack. And that's why the airplane pitches up when it speeds up. If it slowed down, it'd be the opposite story. The angle of attack would increase, and the airplane would pitch down to reduce the angle of attack and regain its equilibrium that way. And in fact, it would settle down to the same angle of attack if it's got enough power, and it would continue to climb at that angle of attack at a steady speed going up. So I hope that's been helpful. I hope you've learned something. We really enjoy it when you come by the Whistle Pig Classroom, and we hope you'll come back and see us again soon. Thank you very much. Take care. Bye-bye.